Hey, so today we're going to talk about our chemical properties of the soil, as well as a few biological. So, we want our soil as farmers, as gardeners, as house owners to be right in the middle. We have our physical properties, our chemical properties, and our biological. We've talked about these already. We're going to move into all of these and all of the biological today. All right, let's first start with pH. So soil pH, which also means power of hydrogen. So y'all can go home to your parents and say, I know what soil pH stands for, and it's powers of hydrogen. That is going to measure the acidity and alkalinity of our soils. We have acidity, which is right here. Everything above 7 is acidic, and everything over here on this side is alkaline, so 8 to 14. Our soil pH ranges from 0 to 14, remember that. And then anything in between here is acidic, anything in between here is alkaline, and right smack dab in the middle is our neutral. If it is 7, which you can see on your papers, it's water, that is a neutral. Everything below that is acidic, everything above that is alkaline. So on your papers, go ahead and write for me in those blanks where you see this gauge here. Acidic is below 7, neutral is at 7, and then everything above is alkaline. A soil is considered alkaline if it is between 8 and 14, and it is considered acidic if it is between 0 and 6.9. Now, we know that lime is going to raise our pH. That is going to send it into more alkaline territory. Sulfur is going to lower our pH. Same with calcium and sulfur. Now I added this fun picture here because you can actually change the colors of hydrangeas. I have some hydrangeas in my backyard, and over the past few years, I've been adding a bunch of stuff, like literally whatever is in the kitchen gets dumped into the hydrangea area. And over time, it's been turning to this pink color, while on the other side where I don't dump stuff, it's turning into that blue. Why? Because lowering and raising the pH can actually change colors of hydrangeas, which I think is very cool. On your diagram, you've got a little symbol for my visual people. Lime, the fruit lime, is going to raise our pH. And eggs, when we smell that really rotten egg smell, that's because of sulfur. Sulfur is going to lower our pH. Now, I added this diagram to your notes because when I first saw this in college, I thought this was the coolest thing that I had ever seen. Now, the ideal soil for us is to have that 5.5 to 7. As you can see, when we start getting a little bit lower into our acidic range, that's where we don't have as much nutrients. Now, we've got a lot of iron and manganese and boron and stuff, but all of our macronutrients, which we'll talk about in a little bit, these super important nutrients, we don't have. Same goes for over here in our alkaline soils. Right here is the perfect balance to maximize all of our nutrients. Now, some prefer, like blueberries prefer like a 5 to 4.5 for reasons I cannot tell you. Let's talk more about our chemicals here. So in your notes, you have a connect the dots. Electrical conductivity measures the salts of the soil. We then have our nitrates, which is a form of nitrogen that plants can take up through their roots. We also, again, have pH, which we know measures the acidity and the alkalinity of our soils. Let's talk about those macronutrients. We've got nitrogen, phosphorus, and potassium. Nitrogen is that M on your diagram. Phosphorus is that P on your diagram. And potassium is K. These are all primary nutrients, and they're found on the periodic table like you learn in chemistry. We need these plants in the greatest amounts. And usually when we see a plant starting to turn yellow and brown, it's probably because they're missing these macronutrients. All right, calcium and magnesium. These are found in the soil when you raise the pH. Raise the pH. That makes the soil more alkaline instead of acidic, like we've got right here. Now, sulfur can be found when you decompose organic matter. And organic matter is just dead plants and animals. That's all organic matter is. So when those dead plants and animals break down, that's when we can find sulfur. Now, our micronutrients are small. Remember, micro means small, macro means big. So we need these in very small quantities. Okay. Roots are the reason that plants have water and plants have nutrients. These roots soak up all of these little ions right here in a solution. So that blank that you need to fill in is roots. Okay, and here's a fun little chart that I have. You're going to match each picture to the definition. So first we have weathering soils and materials. Every rock and mineral that we see here is being broken down over time, smaller and smaller, and eventually it gets so small that the roots can dig or can soak up all those plants. Now, minerals are 45% of the soil, so we need a bunch of those in order for plants to grow. Decomposition of organic matter. I've added a little eaten apple core right here. It was better than a dead deer, but this is just plants and animals decomposing after they die. Fertilizer applications. Here's our little Union fertilizer bag right here. These are synthetic. Synthetic mean that we as humans make them instead of the earth, like decomposition of organic matter. We have our fertilizer applications. Now, I need you somewhere on your notes where there's a blank space to write the difference between amendments and fertilizer. Here's how I want you to do that. Fertilizer is only going to help the soil chemically. It adds nutrients into our soil. Organic matter is going to help the soil structure, that physical property. So we saw when we dig in really hard clay, it's very hard to get that shovel down. If we add organic matter, that's going to make it a better home for our worms and our microorganisms. And then eventually, after a few years, we'll have nice soft soil because of our amendments. Fertilizer does not do that. It only gives nutrients to our plants. Now, I have my little peanut right here. This is nitrogen-fixing legumes. Legumes are a certain family of plants that actually make free nitrogen. So you don't have to buy nitrogen and a fertilizer because these legumes already make it. Peanuts are one of them. We also have atmospheric addition. That is our lightning charges. Our lightning bolts add ions into our soil. I don't know which ions, but they're good. Decomposition of erosion and flooding. I have my little raindrop here. When it floods, think about the hurricanes that we had. A few years back, we had Hurricane Helene, and Hurricane Helene brought a lot of new sediment to certain places. It also took some away. So the soil that's now there has a bunch of different nutrients. And then we have industrial additions like wood ash. That's my little fire. After that, we have our wood ash, and we can add that into our soil. All right. Soils can lose nutrients, and it is not a good thing. It's not a good thing to lose soil. Well, there's two different ways that we can lose nutrients in our soil. One is that they become unavailable, and here's the difference. That's one of your notes questions. Here's the difference between it being unavailable and us losing nutrients. Sometimes the nutrients can be physically in the soil, but they're not available to the plants. It's basically like they're giving silent treatment to the plants. Like they might be in the room, but they're not talking to the plants. Whereas if we lose those nutrients, if we lose those soil particles, they're not even in the room. Now, This is bad for our environment because our plants need as much nutrients as possible. Here are the 5 ways that can happen. We've got runoff, erosion, leaching, gases losses. So think about nitrogen. Nitrogen mostly comes from the soil. It comes from the air. There's a little bit in the soil, but that nitrogen can go back up into the air. And then, of course, crop removal. If you can see right here in this little diagram, when we remove a crop, like let's say corn, if we harvest that corn and we're eating that corn, it doesn't go back into that field. Our waste does not go back into that field. So that field is losing that nutrients from the corn. Okay, here's our fun little diagram. We've got a number here, a number here, a number here, and a number here. I'm going to flip to the next slide for a second. Plant residues and manure, that's number 1 on yours, plant residues. I want you to put that right here. Okay, so we have dead plants and animals. They're going to break down and they're going to add nutrients back into our soil. Number 2 is that fungi and other beneficial microorganisms, they're going to take those dead plants and animals and they're going to start to decompose it. They're going to break it down. Food for them, and then whatever doesn't get used, it's going to be used by someone else. Who is that? Oh my gosh, look, it's the plants. The plants are going to take up all of that nutrients in our roots, and that becomes our number 3 right here. Number 4 is that we have all of our nutrients here. We have potassium, calcium, magnesium, phosphorus, sulfur, and all of these micronutrients. They're going to dissolve, and some of them are going to become minerals, and those go right over here in number 4. I want you to remember that all of this right here is a nutrient cycle. So it goes in and out, maybe sometimes over a year, maybe 100 years, maybe 1,000 years, maybe 1,000,000 years, but it's all a cycle. Matter is neither created nor destroyed. All right, let's get into the fun stuff. This is our biological properties. So again, we have our matching definitions. Soil respiration is when the soil breathes. To respire, take a deep breath in and out. That is to respire. A soil needs to breathe. It takes up oxygen, it stores carbon, and sometimes it releases carbon. We then have our total organic carbon, and that's how much carbon is stored into the soil. That can happen a few feet away, that can happen hundreds of feet away into the core of the earth. Now, we have a problem with climate change because we have a lot of carbon that was originally stored in the soil is in the air, and that's causing global warming. So how can we get all of that carbon that's in the air back into our soil? You guys have the opportunity to solve that problem. And then we have our rhizosphere. Our rhizosphere we're going to talk about in just a little bit, more details to come, but that is the zone immediately close to the plants. That's where the party's going on. So circle which definition is best and pull that to each term. All right. If you can see, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 different people at this party in our biological properties. Now, your notes only have 6. Here's what I need you to do. Pick out your favorite, and I'm going to talk about them, and you write them down. You can draw a picture for my artistic people. You can write the words. You can do hieroglyphics. I do not care as long as you have something written down. Fun fact, did you know that just a little bit of soil, like a whole teaspoon, has millions to billions amounts of microorganisms in there? Think about all that money that you could have in just one little teaspoon if you had the same amount of microorganisms. Let's first talk about enzymes. So enzymes we have in our body, we have in plants, and we have in soils. And they're not really a living thing, but they help out living things. And I would draw them kind of like an E almost, if you wanted to add those, or you can write it down. We have insects and worms. We have fungi, which is also known as mushrooms. algae, cyanobacteria, which is a bacteria, but it produces its own chloroplast, which means not only does it eat things, but it can also make its own food through the sun, which I think is pretty cool. Then we have nematodes, and those are teeny tiny little worms. Some can be good, some can be bad, just depends, but we got nematodes. We have protozoa and bacteria. Go ahead and write down your 6 favorite. All right, let's keep talking about this rhizosphere here. So remember, this is the zone immediately around the plant, so it's right up in here. And what happens, all of this activity is going on because the energy that comes from the sun goes into these plants, and these leaves are going to send it all the way down to the roots, so then it can be stored for the winter and colder times. Well, the microbes, if you look under these microscopes right here, they want a little bit of that action. They want some nutrients, they want some sugars. So they're going to hang out really close to the plants because the plants produce exudates. Exudates, they're released from the roots, and they're food for microorganisms. Now, this can be a beneficial symbiotic relationship, which we'll talk about in a second. There's 2 different things that can happen from there. 2 different bacteria and fungi that play a role. Now, rhizobia is one of those. Here is the underlined stuff that I need you to write. Rhizobia take nitrogen from the air. They then dissolve that nitrogen into the soil and break it down so that the plant can uptake these nutrients from the roots. That's what I need you to write. Air, soil, and plants. And then if you look to your right, there's a diagram. It has a plant and it has bacteria and 2 arrows. And remember, this is a symbiotic relationship. The bacteria doesn't just do it out of the kindness of its own heart. It does it because it wants something. So that plant is giving that bacteria, that rhizobia, nutrients. Stuff that it got from the sun. The bacteria is then in turns giving it nitrogen, which the plant needs. The plants that we're talking about specifically are legumes. That's those peanuts, those clovers, those alfalfas, those edamame, those soybeans. All of these fix nitrogen, make free nitrogen from the air for the plants and the soil. Now, farmers, they harness this ability, and we'll talk about that in our 5.0 crop science unit. So I just talked about all of that stuff for our rhizobia. Remember, this is a symbiotic relationship right here. Our legumes, we need to write that down. Our legumes are the only plant that this can work with. Only plant. Rhizobia has a type. It is committed to our legumes, married to the game. Now we have our mycorrhizae. And our mycorrhizae, they aren't as picky. They're kind of like, they vibe with everyone. They're friends with everyone here. Mycorrhizae is a special fungus that helps the plants get soil nutrients and water. So let's figure out how we can foster that relationship. First, I want to show you guys what it would look like if plants did not have the mycorrhizal fungi. Here's with, look at all of those white roots, healthy, beautiful. Here's without, okay? So this is why it's very important for our plants. Now, here's what we can do to make it better. Here's 5. 1, 2, 3, 4, 5. First, we have to create the right environment for both our crops and our microbes. We're going to add the proper soil nutrients, whatever we need to do to make it a good home. Now, we're also not going to till, because imagine getting your arms chopped off by gigantic scissors. That's exactly what tilling does to our mycorrhizae. We'll talk more about tilling in our next section for our conservation soils, and then we'll also talk a little bit about it in our crop unit. Now, make sure that your irrigation and your drainage is properly situated. You need to make sure that it's getting enough water, that the soil is getting enough water, but not too much water, because then it's going to kill them. You also want to maintain a neutral pH. Remember, that 7 is neutral. And we're also going to incorporate organic matter. Remember, those decomposing animals and plants for energy for our microbes. All right, let's talk about when soils get contaminated. We as humans treat our soils pretty bad. We're going to talk about it, and we're going to talk about how to fix it. So, the definition of soil contamination, and remember, you don't have to write this down word for word as long as you understand it. Soil contamination is either a solid or a liquid of a hazardous substance mixed in with naturally occurring soil. Now we have 2 blanks, and soil contaminants are usually physically or chemically attached to our soil particles. All right, our contaminants, they can hurt us. They can hurt the plants because our plants take them up through the roots, and they can also hurt us and our animals. It's not good for the environment. All right, there are 3 ways that we can figure this out, and there's 3 boxes. Here's what I need you to write. You don't have to write all this definition, but here's what you do in order to clear contaminated soils. First, we're going to remove it. It can be excavated, what have you. What I need you to write down is remove it. Or, number 2, you can leave it. You can leave it. Or, you can contain it. You can contain it. All right? So, we have first, we can take it out. We can leave it and treat it. Or, we can contain it. We can contain the soil and make sure that it does not spread. Those are the 3 ways that we can deal with contamination in our soil. A lot of people use sunflowers. Sunflowers can take arsenic out of the soil. So if you have a soil that's contaminated by arsenic, grow sunflowers. And then you can properly dispose of the sunflowers when the season's over. And after a few years, you should have a clean soil. That is the end of our notes for our biological and our chemical properties.